In this lesson 4.5, we're going to be looking at proving triangles are congruent, and we have three new theorems that we'll be using. So ASA is angle, side, angle. AAS is angle, angle, side. And HL, which is a special triangle theorem called hypotenuse leg. All right, so looking at our first two theorems, the first one is angle, side, angle. And so remember that the name of it tells you kind of how it has to be ordered. So in order to follow angle, side, angle congruence theorem, you have two triangles that have two sets of congruent angles, and the included sides are congruent. So if you look at how it's laid out, it's angle, and then the side in between, and the other angle. So angles, and then the included side. So angle, side, angle, and it has to follow that exact same order in the second triangle. So angle, side, angle in both, then the triangles are congruent. The next one is angle, angle, side. So here we have two angles that are congruent in both triangles, and a non-included side. So the side is outside of those two angles, not the one in between them, and that would be angle, angle, side. And if you have those two sets of congruent angles and the non-included side is congruent, then that would follow angle, angle, side congruence, and the triangles are congruent. So we still have our old theorems and postulates, our side, angle, side, and our side, side, side. So with those extras, we have 5 total triangle congruence theorems, and we're going to see if it's possible to prove that two triangles are congruent. So in example 1a, here I have two triangles, and both of them have two sets of congruent angles shown and one congruent side. So in order to follow triangle congruence and to use one of these, they have to be in the same order. So based on how this first triangle is set up, we have two angles and the included side. So this one is set up as angle, side, angle. In the second one, we have two congruent angles, but the side is outside. So this one is set up as angle, angle, side. So since these don't have the same order of those congruent pieces, this one is not possible to prove that they are congruent. We don't have enough information. So we would have to have something else extra to prove that those were congruent if they are. All right, in our second one, here I have two angles and a non-included side. So this one is going angle, angle, side from 1. So angle 1 to angle 2 to side 1. So in this other one, we still have two angles and a non-included side, but let's make sure that the non-included side is attached to that same angle. So notice that it comes from the angle that had two markings. Same thing here. It comes from the angle that has two markings. So these are set up in the same order, even if they are in different orientations. It's flipped over. It still follows that same order from angle 1 to angle 2 to side 1, angle 1 to angle 2 to side 1. So this one is yes, and we would use angle, angle, side to prove that those were congruent. All right, so here we have our first proof. And so we're given that angle B is congruent to angle C. So as we write it in our proof, we can mark it. Angle B is congruent to angle C. Angle D is congruent to angle F. And M is the midpoint of DF. So all of these have been put on the same line as my givens. Two of them give me angles, and one of them I have to use further. So the one that I have to use further says that M is the midpoint of DF. So we've been using midpoint a lot in this unit so far, and what we use whenever we see the word midpoint, or the abbreviation for midpoint, is we think about the definition of that term. So the definition of midpoint says that if a point is a midpoint of a segment, then that segment is split into two congruent pieces. So since M is the midpoint, the two congruent pieces that are set up are DM and MF. So this next statement will be that segment DM is congruent to segment MF. So now if I look at my diagram and I think about the theorems that I have, so these are set up as angle, angle, side. So the side is outside of the two angles. Angle, angle, side. It follows that same pattern in both, angle, angle, side. And so that is one of our congruence theorems. We have enough now to say that the two triangles are congruent by that theorem. So that's the angle, angle, side, triangle congruence theorem. And since this is my prove statement, I'm going to take that exact statement that they told me. So it should already be lined up based on the corresponding parts. Triangle BDM is congruent to triangle CFM. So we have the two angle statements and a segment statement to make up angle, angle, side. All right, in our next proof, here we have WZ, the segment bisects angles XZY and angle XWY. So we're going to look at those two angles and what this word means. So this was my given, and within my given, the term bisect shows up. So for bisect, we have a definition, the definition of an angle bisector, which is similar to the definition of midpoint, but it's not just a point, it's a whole bisector. So the definition of an angle bisector is that if a segment, a line, a ray is an angle bisector, then it's going to split that angle into two congruent parts. So two angles were bisected here. Let's look at those individually. So the first angle that was bisected was angle XZY. So this bisector is going to split this angle into two congruent parts. So the two congruent parts are XZW and WZY. So we're going to write those two angles as congruent. So angle XZW is congruent to angle WZY. And then there was another angle that was bisected. So let's go back to our diagram. I'm going to go in and mark that one in orange since we talked about it. So these two angles have been proven congruent. The second angle that is bisected is angle XWY. So this angle is bisected. Let me scoot that up to match a little better. So the two angles here are angle XWZ and angle ZWY. Those two angles will be congruent based on that definition of an angle bisector. So angle XWZ is congruent to angle ZWY. So I'll take that extra stuff off, just try to clean up my picture. So now I have two angles that are congruent, and I need to come up with a side congruent statement, but I don't have any more to use from my givens. So since I ran out of information from my givens, I'm going to go to my diagram. So if I look at my diagram and I'm thinking about these two triangles, let me bring this down a little bit. So these two triangles, when I'm looking at triangles, there are a couple things that I can look for that can be used even if there's no other information. So the two things we look for are vertical angles, which are at the intersection of two segments, and I don't really have that here. Or I look for a shared side. So if I look, I notice that this side shows up in both of those triangles. So I can always say that a side or a segment is congruent to itself. So I'm going to need that here to get that third piece of these triangles to line up. So that's going to be segment ZW, and I'm going to say that ZW is congruent to itself. And the property that I use there is the reflexive property. So if you have a shared side, that's going to be using the reflexive property, and we do that from the diagram. So now I have two angle congruent statements and one side congruent statement. I need to pay attention to how it's arranged to know what theorem I'm using to prove this. So based on the location of the two angles, the side is the side that connects those two angles. So this one is arranged as angle, side, angle. So that's going to use the angle, side, angle, triangle congruence theorem. So it's all about how it's arranged and how we can use it. All right, so in example 4, we're given two congruent statements, and we need to state a third congruence in order to prove that these triangles are congruent by the given method. So the first thing I want to do is I want to draw my two triangles, and I'm going to label them. So this will be PQR for the first triangle and STU for the second one. So I just want to label my triangles, and then I'm going to mark the congruence statements that were given. So the first thing I was told was that angle R is congruent to angle U for this first set. So R is congruent to U. And I was given that PR, the segment, is congruent to SU. So far I have a side and an angle in each of these triangles. The theorem that I want to use is angle, side, angle. So that means that there are two angles in the included side. So in order to figure out which angle congruence I need to finish this off, I am going to look at the arrangement. So in order to go angle, side, angle, I need angle P in the first triangle. And then if I go angle, side, angle, I need angle S in the second one. So the third statement that I need is that angle P is congruent to angle S. So that'll finish off angle, side, angle for me. So looking at this next example, we're still using those same triangles. So PQR is congruent to STU. And I'm going to mark the things that were given to me. So angle R is congruent to angle U, is my first congruent statement. PR is congruent to SU. So we have the same setup as we did in the previous one, but this time we need to use angle, angle, side. So I have a side and I have an angle in each of these, but here the angles are together and the side is not included. So of these, if I have the side and the angle, I need another angle to complete this statement. And I just think about like which of these two would make it go angle, angle, side. So I want the side to be the non-included side. So in the first one, I need angle Q to make it go angle, angle, side. So I'm going to say that angle Q is congruent to angle. So in the other one, to complete that, the last thing I need, the non-included side, would make it angle T in this second triangle. So if I used P and S again, that would make S be make the segment be the included side instead of the non-included side. So angle Q is congruent to angle T would help me complete this proof by angle, angle, side. All right, so there is one theorem that you might wonder about why we don't use it, and that is side, side, angle. So it's always starting with whatever you have more of. So you have more sides, so it would be named side, side, angle. And so there's a reason it doesn't work besides the fact that it spells a bad word if you reverse it. So the reason it doesn't work is shown here. Here are two triangles that follow side, side, angle. So we have congruent sides. So one side is 5 centimeters, the next side is 6 centimeters. And then we have a congruent angle. So looking at these two triangles, remember that congruent triangles, by definition, have 3 congruent sides that correspond and 3 congruent angles that correspond. So it should be the exact same size and shape of triangle. If you look at these two triangles that have been created with these stipulations for side, side, angle, and if you look at them, do they look like the same triangle? Like you could lay one on top of the other and it would be the same. And it does not. So since the angle is non-included in these sides, there are 2 different arrangements that you can make that can complete that triangle that are not the same. So using side-side angle alone is not enough to create two congruent triangles. So these triangles that were created with this criteria are not congruent. So there is only one formation of side-side angle that works to prove that triangles are congruent. And so side-side angle only works in right triangles. So in order to use this theorem, it's going to be in a right triangle. So instead of using sides and angles, it has a different name, because since we're working with right triangles, we're going to talk about it in terms of hypotenuse and legs. So the hypotenuse leg congruence theorem is the only formation of side-side angle that works. So we use HL for this one. So what I always tell my students year after year, these are my initials, HL, and it only works in right triangles, so just remember, Holly Lawrence is always right. So if you think about that, you can remember HL for right triangles. Holly Lawrence is always right. It's a good rule for life. All right, so in the hypotenuse leg congruence theorem, in two right triangles, so we need to know that both of the triangles are right triangles. There needs to be one angle that's a right angle in each triangle. So in two right triangles, if the hypotenuse of each triangle are congruent, and one set of legs are congruent, then the triangles are congruent. So if the hypotenuse of each triangle is congruent and one set of the legs are congruent, then that is enough to say that this will be a set of congruent triangles. With a right angle, there is no other way that you could form another triangle that would be different. So with a right triangle, this is the only configuration of side-side angle that sets up for congruent triangles. So you have to have the hypotenuse of each triangle being congruent and one of the legs in each triangle being congruent to each other. So hypotenuse leg works only for right triangles. So using all 5 theorems that we've looked at so far, we can look at these triangles and decide if there is enough information based on the markings to prove that they're congruent. So in this, one thing I notice is that I have a perpendicular marking. So that means that both of these sides are going to be right angles if it's perpendicular. And another thing I notice is that there is a shared side. So always try to think about all the information that you can see. So since there's a shared side, that's going to be congruent to itself. So if I look at the marking, I know that I'm dealing with right triangles. So if I look and I notice that this is set up as side-side angle, we don't use side-side angle. In right triangles, we use hypotenuse leg. So this one does have enough information, yes, because I have the hypotenuse of each triangle and a leg that's congruent in each. So this is using hypotenuse leg. All right, in this next one, I notice right triangles again. I notice perpendicular, so they're both right triangles. And again, I have that shared side. So if I look at this one, the configuration of this one, the angle is between the two sides. So if I think about them in terms of just a regular triangle with sides and angles, I notice that it's as side, angle, side, because the angle is in between. So another thing is, if you look at the right triangle and you think about it in terms of hypotenuse and legs, the hypotenuse is not marked as congruent. They're both legs. So instead we use one of our other theorems for this one, and this is going to be side, angle, side. So it's side, angle, side for each one. So this one is yes by side, angle, side. So since we didn't have the hypotenuse, we can't use hypotenuse leg, but we do have enough to use side, angle, side, which is another congruence theorem. All right, so looking here, I have two sides that are marked congruent, and I have an angle. But the angle is not included. So this is trying to use side, side, angle, which is not a thing. And the angle that I was given was not a right angle. So side, side angle only works in right triangles, so this one is a big no. This one cannot be proved congruent unless that angle that's given is a right angle. All right, we have one last proof to go over. All right, so here we're given that D is the midpoint of CE, that BD is congruent to FD, and that angle BCD and angle FED are right angles. So part of this proof is set up for us, and the first thing is that it only used one given at a time. So D is the midpoint of CE. That is a given, one of our givens here. And so if D is the midpoint of CE, every time we see this word midpoint, what we've been using is the definition of midpoint. So the definition of midpoint says that if a point is a midpoint, it splits it into two congruent segments. So the segment CE is the segment that was using the midpoint. So the two segments that will be congruent are CD and DE. So CD will be congruent to DE. So once I put that in my proof, I mark it and I move on. All right, so now I have one set of congruent sides. All right, here I'm introducing my next given, and it goes on and puts both of these together. So side BD is congruent to side FD. So BD is congruent to FD. And it says that BCD and FED are right angles. So those were both givens. So now if I know that there is a right angle in each of the triangles, the next thing I can say is that those two triangles that are formed with those right angles in it, so BCD as a triangle this time, and triangle FED are right triangles. So that is going to be from the definition of a right triangle. A right triangle is a triangle that has one right angle in it. So now I'm dealing with right triangles. I have a leg of each, and I have the hypotenuse of each. So I'm able to say that these triangles are congruent by the hypotenuse leg triangle congruence theorem.